Electric field due to infinite conducting plate of positive or negative charge. I love this. It's one of those physics things where you think you've got an infinite plate, and they indicate infinite by having all the squiggly line on there, and there's no such thing as an infinite plate. Of course a plate can't be infinite. But anyway, you can see that the top plate is going to be positively charged because the arrows of the field lines point up because the positive test charge will go up, and the bottom plate is negatively charged because the arrows point down because the positive test charge would want to move towards the plate. And you can see that these plates are uniform because all the arrows are approximately at the same. Okay, back to it. Alright, that's recording again. Yeah, anyway. Uniform lines and stuff indicates uniform distribution of charge. And of course, if you put any charge onto any object, whether it's positive, which is a lack of electrons, or negative, which is an abundance of electrons, it's going to array itself as far apart as possible and from each other, each piece of charge. And so the best way to do that is to array themselves evenly. Two infinite oppositely charged parallel plates, then the field lines will go between them, and they're going to be equally spaced. And again, you can see the arrows going from the positive to the negative, and wonderfully that means that if you stick a charged particle and fire it in sideways, it's going to be affected. So say, for example, you fired an electron in here, the electron's going to experience a attraction to the positive plate and a repulsion from the negative plate, and consequently its path will bend. And guess what? Guess what formulas are coming back? It's right angle triangles and all the kinematics formulas, and at some point a bit of a uniform circular motion, because all the crap at the start just comes back again. And they'll probably find a way to get relativity involved here too. Of course, you know, it's the electric fields which accelerate electrons in the Large Hadron Collider and the Australian synchrotron. Oh, no, hadron is protons, and I think that's it. Anyway. Two infinitely finite, this time, finite oppositely charged parallel plates. So again, the arrows move in the direction as stated, positive to negative, because positive test charge would be repelled from the positive and attracted to the negative. But near the edges, that you don't get that uniform field lines going on. You get a bit of curvature at the ends there. Electric field lines for hollow conductors. So the charges are all on the outside of the sphere. That's why if you looked at that video with hollow conductor on the main page and they scooped the electrons from the outside, it worked, but when they scooped it from the inside, there was nothing there. Well, that's because there's no electrons on the inside. Unless you actually put a charge on the inside physically, there are no field lines on the inside. They're all on the outside. So it's kind of like a point charge, except that there's a big hollow sphere in the middle. You got your positively charged example on the left with the arrows going out, and your negatively charged on the right with the arrows coming in. And as you can see, the amount of lines per unit area that you have closer to the sphere are a lot closer, and that means a more intense electric field. And as you go further away, they're a lot further apart, and so the strength of the field reduces. The lines always leave at 90 degrees to whatever point they're coming off. If you stick a hollow uncharged conductor between two charged plates, it acquires a charge as the electrons in the metal move due to the attractive forces from the two charged plates. So you can see here the field lines being drawn towards the negative and then going down from the positive there. And as you can see, when you stick this like rod through, it warps the field lines on the left and the right there, but all the electrons are attracted to the surface up the top, because that's where the positive plate is, and all the positives as a result will be left down the bottom. It's not that the positives are attracted to the negatives, because that's like protons, they're in the metal atoms, they're not going to move anywhere, they're stuck where they are. But the electrons are able to flow because it's a conductor. So the electrons abandon all the atoms down the bottom and move to the top, and that's what leaves the positive charge down the bottom. The field lines warp, as you can see. Now this is there's a little thing you can get from MIT. I looked at the price. It was like $4,000 or something. You stick one of these on the overhead projector. I need to find one that we can use. All these little iron filings that you see there, they're all suspended in a gel, so they're able to move and adopt positions. And that's a little piezoelectric gun, so it's got that crystalline substance that you can create an electric spark off. Man, one day I'll have to learn how that works. Anyway, you can stick the little nib that generates the spark onto one of those two metal plates there, and it'll end up charging one plate or the other. And so you can make one positive or make one negative relative to what you want to do. Now here we can see the apparatus has been changed to show two, these will be oppositely charged plates. You can see the lines going straight up and down in the middle, and then you can see the curvature on the left and the right there, which is kind of cool. This one here is one would be charged negative and the other positive. I'm going to assume the one in the middle is negative. Of course, you know, it's not going to be able to actually tell that unless you were able to see a positive test charge there and see which way it went. Then you're not going to know which point is negative or which is positive. But you can see the straight lines connecting the point charge in the middle to the disc on the outside. This one's supposed to demonstrate how there's no charge in the middle and therefore no field lines. So you can see that the middle disc and the outer disc, they're charged, and it's creating those sort of field lines between the two. But in the middle, you don't see a cross, and there's a bit of something going on around the inside of that metal ring. But to be honest, if it really did have field lines going through the center, all that stuff in the middle there wouldn't just be sitting around uniformly sort of placed there. You would see lines forming, and there's none. So that's a demonstration of the fact that in the middle of the conducting sphere, there isn't any field lines, unless of course you go out of your way to put a charge inside. Not sure how you'd go about that. You know what? You can Google it, Daniel, and teach me. These guys like charge points. So I can only assume that they've put electrons on both of them, and consequently you can see the two fields pushing on each other there. They've got that whole bendy get away from me thing going on in the center. And then if we look at unlike charge points, you get a positive and negative there, you can see the fields attracting. So they're pulling on each other, they're pulling towards, and the field lines just look like what they do in the textbook, which is kind of cool. The last thing was the Faraday cage, and that is, if you want something that's going to prevent you from getting an electric shock, then one of the best ways is to put yourself into a cage, like a Faraday cage, which will then prevent any chance of an electric field going through it. It's also one of the ways they sort of lock down top secret areas, and yeah, I guess it's used for art and whatnot. David Blaine got stuck in a Faraday cage. I'll stick the video up. MIT charging a hollow tube, you've seen that. I'll put up this Faraday cage video, and the last thing you got to look at is electric field lines near a sharp point. So you saw in the circle and the sphere that they all leave at 90 degrees, and they'll be sort of uniformly arrayed. But then when you provide a sharp point, all the charge gathers at that sharp point, and the lines get very, very thick. Well, there's a lot of them there. And that puts a lot of force behind the, there's a lot of build-up of charge, and so consequently it's at the sharp point where you can start to get that leakage of charge. It's one of the reasons why spark plugs have a sharp point, because that's where the lightning comes off, like the shock that ignites the fuel. There's a good video on it about putting forks in the microwave, which I'll be able to show you in a tick. So a really nice point is going to allow for charge leakage. The gradual discharge is called corona discharge, which is wonderfully appropriate for this time. Corona electrodes are used to create an ionized air particle arrangement. If you look inside the tube, like the helium tube we lit up the other day in class, it doesn't have a big flat disc there. The discharge across the tube comes from a point. I'll put up a picture of that if I remember. What's this? High voltage power source and the corona effect? Yeah, I'll find that video, maybe. The other interesting thing is St. Elmo's fire. When you build up a buttload of static electricity, from a sharp point it can actually bleed off and that causes the air around. Well, it's not the charges that you see, but rather the ionisation of the air that results in visible light, and it's known as St. Elmo's fire. Used to be like a magical thing that people saw at the tops of ships and masts long time ago. Now we understand what it is. It's not magic anymore, but yeah, you can see the St. Elmo's fire at a meteorological observatory here. It's got this really weird, spooky purple glow. I'll see if I can find some decent footage of it. For some reason I can't seem to find it. The application is a laser printer. I'm not sure if that's still the application. Where did I put the damn physics book? I don't know if I still got it here. I think the physics book is outside in my lounge. Oh no, there it is. Let's have a look at the chapter on electric fields. I'm looking right now. I am at page. Motion charge particles in electric fields. I didn't think the laser printer was. So, applications of corona discharge, the lightning rod. Okay, so it's got the corona discharge picture on page 124, and it goes on about corona discharge. I'd encourage you to go and have a read of all of that. It's also got a QR code with a link. Helpful online resources, polar and non-polar molecules. Is it polar? Okay. It's a bit chemical really, but whatever. Electric fields are strongest near the sharp points of conductors. I'm reading from page 113 here. Sketch the electric field produced by a charged pear-shaped conductor. Describe how the large electric field in the vicinity of sharp points may ionise the air. Okay, cool. So, used to have the application of how a laser printer worked, but that's no longer the point. Ignore those questions. That's it for electric fields. I'm just going to post a bunch of relevant videos and maybe a few notes on how they're relevant. Other than that, just go ahead and do all the questions in your book, please. Thank you and good night.